Hello everyone! In this video we will continue to examine topic 7.3, the structure of matter, and in particular we will begin to unpack Feynman diagrams. Alright, so the first thing I'm going to do actually is slide back here and just clarify something I said in the last video. So our best understanding right now is that gluons are actually massless. And so the range of the strong interaction is related to the range, in some ways, of the residual, or what we think of as the residual strong interaction, and therefore related to the mass of the particles that mediate the residual strong interaction, which we'll get to in a bit. So strictly speaking, the range of the strong interaction as it applies to quarks is infinite, with the major caveat that that interaction is simply an interaction only between quarks, and that quark confinement or color confinement restricts all such interactions to be sort of at the scale of a nucleus. If it were any longer, quark confinement would cause other quarks to pop into existence. So, given that, let's return to Feynman diagrams here. And Feynman diagrams, more formally, are diagrams which show particle interactions. They have both time and position axes. Unfortunately, different books and different resources will have time and position on alternative axes. So you will often, but not always, find position on the vertical axis and time on the horizontal axis. If that's the case, you simply need to read your axes carefully and interpret them correctly. So the diagrams that I will be drawing in general will have time moving forward, sort of up the page, and I would always recommend glancing at those axes to make sure that you understand which direction time is flowing in the particular diagram that you're drawing. Particles, so real physical particles, are represented with straight lines, as shown. Exchange, or virtual particles, are represented by wavy or dotted lines, depending, as shown here. And those are indicative of the kind of interaction. So I'll be representing electromagnetic interactions with the wavy photon here, and then strong is a little bit complex, so we'll get that to a bit, but weak interactions are always mediated by a dotted line and one of the weak bosons. So in this particular Feynman diagram, a photon is mediating the electromagnetic interaction between two electrons. In this particular diagram, we're actually showing nucleons interact. So you are not restricted to using Feynman diagrams only with fundamental or elementary particles. You can use a Feynman diagram to demonstrate an interaction between composite particles as well, in this case hadrons. And what this is showing is a neutral pion being exchanged in order to mediate the residual or strong interaction between hadrons. Believe it or not, this is exactly the kind of interaction that keeps protons and neutrons stuck together in the nucleus. As it turns out, this exchange particle is not one of the gauge bosons we discussed last time, but the residual strong force is mediated by these mesons. So neutral pions, positive and negative pions included. It's important to note that when drawing Feynman diagrams, at each vertex, so this is a vertex right here, conservation of charge, lepton, and baryon number must be applied. So charge, lepton, and baryon number are applied directly at a vertex interaction. But it is important to note that you will often find that conservation of energy or mass is violated in the vertex interaction itself. Okay, so for example, the most obvious case right over here, when this electron emits this photon, it is not necessarily the case that this electron has lost energy. And in fact, in this particular interaction, it has not. How is this allowed? Well, for very small delta t, and so this is why the lifetime matters, then in accordance with the Heisenberg uncertainty principle, delta E can be quite sizable. So for small delta t, you can have significant delta E. And as a result, right at these vertices, you have temporary violations of conservation of energy / conservation of mass. On the other hand, at the vertices, the conservation of charge, lepton, and baryon number all apply directly. One bit of vocabulary, as mentioned before, these interior particles are known as virtual particles. Virtual is not just a synonym for exchange particle. Virtual highlights another feature of these guys, which is that they cannot be detected. So the virtual part is that they can't be detected. The exchange part is that they are exchanged between these incoming particles. So this proton and this neutron have their interaction mediated by the exchange pion here, which is a virtual particle because you cannot detect it.